All right, so in the last chapter, we found the intersection of two lines by a couple of different methods. We used the method of substitution, and we also used the method of elimination. And in this chapter, we're going to learn some more sophisticated methods for solving systems of linear equations. All right, so when we find the intersection of two lines, we're solving a system of linear equations. We have more than one linear equation, and we're trying to find the x and y values that satisfy both of them. And the method that we're going to learn today is called GaussJordan Elimination. Now, GaussJordan elimination can seem a little cryptic and very mysterious. So what I want to do is show you an example side by side. I'm going to show you the method of elimination and GaussJordan elimination and hopefully take some of the mystery out of it. So let's take a look at this system of equations that we have here. 2x plus 4y equals 8 and 3x minus 5y equals 1. Now, the idea behind the method of elimination is just to use the rules of algebra and manipulate these equations to eliminate a variable. And so when I look at these two equations, the first thing I see is that there's a common factor of 2 in every term of the first equation. So what I can do, I know that one of the rules of algebra is that if I do the same thing to both sides of an equation, the equation is still true. So I could just divide both sides of the first equation by 2. Or you could think of it as multiplying both sides by 1/2. And when I do that, I get x plus 2y is equal to 4. Right? Just divide every term by 2. And I'm not gonna change this second equation at all. I'm just gonna write it down as it is. All right. So this is a little bit different than the normal method of elimination because I'm going to continue writing both sets of equations as I manipulate them. Okay, that'll help me show you and compare this method of elimination with GaussJordan. So, all right, so now I need to eliminate a variable. And I can see that if I multiply the first equation by a -3, I'll be able to eliminate the x variable. All right, so I'm going to multiply this first equation by a -3. All right, so I get -3x minus 6y. I'm just multiplying every term and distributing it across all the variables. And then again, I'm multiplying by -3, so this becomes -12. Okay, just multiplied everything by 3. And I'm just going to leave the second equation as it is. So I'm just going to copy it down as it is. Equals 1. All right, so now I see that if I add one equation to the other, if I add the first equation to the second equation, I'm able to eliminate a variable. And I can add the first equation to the second equation because I've got a statement that says that these two sides, these two things are equal. And so if I add equal things to both sides, then I haven't violated the rules of algebra. So I'm going to leave the first equation as it is, minus 6y equals -12. And then I'm just going to replace the second equation with that second equation plus the first equation. All right, so 3x plus -3x just becomes 0. So I can kind of skip writing that. I have -5y plus a -6y becomes a -11y. And 1 plus a -11 becomes a -11. All right, now you can see that second equation. I can divide both sides by a -11, right? And then I'll have y. So I'm going to do a couple of things in this step. I'm going to divide out. I multiplied by -3, but now I really don't need that -3 in there anymore. So I'm going to divide the first equation by -3. So I get x plus 2y equals 4, right? So I'm back to the same equation I had before. But I'm going to divide the second equation by -11, right? So that I get y is equal to 1. All right. Now, ordinarily you'd say, okay, y is equal to 1. Yay, I've got it. And I can just plug it into the first equation and solve for x. But we're going to go through this process, and we're actually going to eliminate now the y variable in the first equation. Okay, so this is a little bit different than what we've done before. But again, I'm just showing you. we're gonna be able to compare this to the GaussJordan method. So the next thing I'm going to do is I'm just going to leave this equation as it is. Okay, and then I see that if I multiply the second equation by a -2, right? Just multiply both sides by -2. Now when I take the first equation and add the second equation, I can eliminate the y variable in the first equation. All right, so what I have then is x, because there's no x term. So I'm just adding this -2y to the left side of the first equation. So then this becomes 0, right? 2y minus 2y just becomes 0. And then the x doesn't change because there is no x term. And then I'm going to take this -2 and add it to the 4. So I get 2. All right. And then I can also just divide out that -2 again. So then I just get back then y is equal to 1. Okay. So hopefully you followed all that. So that's the method of elimination, only we kind of went through the full elimination instead of stopping at this point when we got y is equal to 1 and then using substitution. So because that's kind of a hybrid between elimination and substitution. So we kind of did a full elimination method here. And we find that x is equal to 2 and y is equal to 1. All right, let's talk about GaussJordan elimination. Now, GaussJordan elimination uses something called an augmented matrix. So it's just really a shorthand way of writing this system of equations without having to carry along all these x's and y's and equal signs. Basically, what we're going to take is the coefficients from this system of equations and just worry about those, really, because if you look at all the way down, we're just carrying around along this x and this y and the equal signs. We don't need all that. We're going to strip this down and just deal with the coefficients. So I'm going to write this first system of equations as just 2, 4, 3, -5, 8, and 1. And I'm going to draw a line here for where the equals would normally be. Okay, so I've eliminated all the x's and y's. So essentially this first column corresponds to the coefficients on the x terms, and the second column corresponds to the coefficients on the y terms, and then this last column just corresponds to the stuff on the right hand side of the equation. And this is called an augmented matrix. Okay, augmented matrix. Okay, now why it's called an augmented matrix will probably become more apparent as the course goes on, but essentially just think of it as just a kind of an array of numbers, right? We're just keeping the numbers around, eliminating all those other symbols. All right, so what I can do all the way down here is just write the augmented matrix corresponding to the system of equations I have here on the left hand side. So if you look at this next one, if I just write the augmented matrix for it, I get 1, 2, 4, 3, -5, 1. Okay, and then I'm going to draw a line. So that's the augmented matrix corresponding to this second set of equations here. Now, what did I do between those two sets of equations? I basically just took the first equation and divided everything by 2. Now, if you look at this augmented matrix, you can think of that as taking row 1 and taking half of it. So I basically took half of row 1. All right, so I'm going to note that here. That's what I did. Okay, so GaussJordan basically takes an augmented matrix and performs row operations on it. Okay, we're going to perform row operations on it. Now, but those row operations really correspond to things that we could have done with the original set of equations, right? So I can take 1/2 of the whole equation, right? I can just multiply both sides by 1/2. That works. So I can also multiply a row by a constant, because that's equivalent to just multiplying both sides of one of the equations by a constant. And that's a valid algebraic thing to do. All right, so the next augmented matrix corresponding to this set of equations is -3, -6, -12, 3, -5, 1. Okay, so what's the row operation I performed? Well, if you look at the original set of equations, what I did is I multiplied the first equation by a -3, right? So I just multiplied both sides by -3. And if you look at it in terms of the row, what I did is I took row 3 times row 1 times a -3. Okay? So again, I'm just writing it in terms of row operations. Okay, writing what these algebraic things that I did to the system of equations, writing them as row operations. Okay. This next set of equations, all right, I have -3, -6, -12. And then there is no x term. So I'm going to just make that a 0 because it's like 0 times x. And then -11, -11. All right. So that's the augmented matrix corresponding to this set of equations here. So what did I do? What did I do? I took row 2 and I added row 1. Right? And I could do that algebraically. If you look back at the original equations, I did that because I'm just adding equal things to both sides. All right. And so let's look at the next set of equations. All right. Now the augmented matrix corresponding to that set of equations is 1, 2, 4, 0 because there is no x term, and then 1 because the coefficient on y, if it's just y, is just 1 times y, and then 1. Okay. So this is now my augmented matrix for that system of equations. So let's think about think about it in terms of row operations. Now I took the second equation and divided it by -11, where I multiplied by 1/11, -1/11. And I also divided the first equation by -3, or you could think of it as multiplying by -1/3. So I actually did 2 row operations here. I took the first row times a -1/3, right? -1/3 times row 1. Okay, so I'm using R1 to designate row 1. And then I took the second row and I multiplied by a -1/11. Whoops, 1/11 times row 2. Okay, so I really did 2 row operations in one in that step. Okay, so now again we can write the augmented matrix corresponding to this next set of equations. 1, 2, 4, 0, -2, -2. All right. So what did I do from one equation to the next, or one augmented matrix to the next? I basically took the second row and multiplied by -2. So -2 times row 2. All right. Which is just equivalent to taking the second equation and multiplying both sides by -2. All right. Now, finally, our last equation looks like this. We only have the x term, so we have 1 times x, and 0, the y coefficient is 0 because we don't have a y term. And then we have 2, and then in the second equation we don't have an x term, but we have a y term, so 1 times y, and then 1. Okay, so there's our augmented matrix. And what did I do? I just took row 1 and I added row 2, from the previous augmented matrix, row 2. I just added row 2. So I replaced row 1 with row 1 plus row 2. And then I took the second row and I multiplied by -1/2, or you could think of it as dividing by -2. Okay, and then you can see that my augmented matrix is essentially saying that x is equal to 2 and y is equal to 1. If I took the augmented matrix and turned it back into a set of equations. All right. So let's just get to give you a little flavor of what the valid row operations are in GaussJordan elimination. So my solution for this example is that x is equal to 2 and y is equal to 1. Now, it never hurts to check these things. All right, so let's look at the original equations. It was 2x plus 4y equals 8. So 2 times the x value I found plus 4 times the y value I found is equal to 8. Is that true? 2 times 2 is 4. 4 times 1 is 4. 4 plus 4 is 8, so that works. The second equation was 3x minus 5y equals 1. So 3 times the x value I found minus 5 times the y value I found equals 1. Is that true? 6 minus 5 is 1. Okay, that works too. So this is my solution. I can validate that solution that is an x and y value that satisfies both of those equations. All right, so let's take a look at what the valid row operations are. This is an important thing to remember. There's just 3 of them. Now, the first one is one that we didn't really touch on up here, but I think it's fairly straightforward. You can interchange 2 rows, any 2 rows. Interchange what? Interchange. Hang on. Interchange any 2 rows. Okay. So, and that makes sense, right? Because it doesn't really matter what order I wrote these equations in. I could have written 2x plus 4y equals 8 second. I could have had 3x minus 5y equals 1 and 2x plus 4y equals 8. It's the same system of equations. It doesn't matter what order the equations are listed in. So interchanging 2 rows seems like a pretty straightforward operation that you could perform on the rows of an augmented matrix, because the rows of that augmented matrix corresponds to equations. And the way that we note an interchange of 2 rows, if we interchange row I with row J, we just write it like this. I kind of use the little double-ended arrow. Okay. The second row operation that we can perform is to replace any row with a non-zero constant multiple of itself. All right, so you can see we did that several times up here. We took 1/2 of row 1. So we basically took row 1 and replaced it with 1/2 of row 1. We took row 1 here and replaced it with -3 times itself. We took -1/3 of row 1 and so on. We did that several times here. And so the way that we denote that is just use whatever the constant multiple is, whatever, let's call it C in the general case, Ri. So, so this I and J can be row 1 or row 2, or if we have more than if we have more than 2 rows, it could be row 3 or row 4. So that's just designating the row number, and then the C is whatever the constant multiple is. So, like in this case, the constant was -2. All right, one more row operation, valid row operation, and that's to replace any row by the sum of that row and a constant multiple of another row. All right, so we did that a couple of times as well. Now we did it in 2 steps in some of these cases. For example, here, when we went we multiplied row 1 by -3, and then we added row 1 to row 2, and then we went back and we divided out that -3. So we multiplied by -1/3. So we ended up with what we had originally. Now we could have done that in one step. We could have just taken -3 times row 1 in this case and gone straight to here, right? We could think of this as being negative, let's see, so we replace row 2 with row 2 minus 3 row 1. Okay, we could have done that whole thing in one step. And so that's what we're doing in this particular row operation, is we're replacing any row by the sum of that row and a constant multiple of another row. And we can denote that as Ri being the row that we're replacing, plus A, which is the constant multiple, times Rj, okay, which is the row that we're multiplying by. Now, I tend to think of GaussJordan as like a game. All right. Just like in chess, your pieces have certain legal moves, and your end goal is to capture the king, right? Now in GaussJordan, you have these legal moves. That's it. These 3 legal moves are all you can do. These are your legal moves, and your end goal is to create a matrix that looks like this one, right? That looks like, on the left side, looks like 1, 0, 0, 1, and then with some numbers on the other side, right? Because that corresponds, that tells you what X and Y are, all right? So your end goal, if these are the legal moves, is to create a matrix that looks sort of like this: 1, 0, 0, 1, with some numbers. I'm just going to put asterisks here just some numbers. You're going to have some numbers there. All right? This is your goal. You know you won the game when you get to something that looks like that. All right? So, we're going to play this game today, and hopefully hopefully it'll be fun. All right. So that's all I have for this video. I'll meet you in the next example.